Hello friends, I Dr. Minal Harde from Department of Pharmaceutical Chemistry, PE Society's Modern College of Pharmacy, Nigri. Welcome you all in today's session. Today as we are going to see UV visible spectroscopy part 2, in the last section we have covered part 1, that is Introduction to UV visible spectroscopy, Principle, Instrumentation. In today's part we are going to cover Lamberts law, types of transition in organic molecule and application. To start with the Lamberts law, the scientist says when a beam of monochromatic light passes through a homogeneous absorbing medium, the rate of decrease of intensity of radiation with thickness of absorbing medium is directly proportional to the intensity of incident radiation. Scientist says when a beam of monochromatic light passes through a homogeneous absorbing medium, the rate of decrease of intensity of radiation with thickness of absorbing medium is directly proportional to the intensity of incident radiation as well as concentration of absorbing solution. Scientists Beers and Lamberts, they have combined and prepared an equation that is A equal to ABC. This is a very important equation where A stands for absorbance. Absorbance has no unit. Small a or absorptivity, it is the molar absorptivity. Then B is the path length of the sample, it is in the centimeter. Then C is the concentration of the compound in solution. It is expressed in mole per liter. This is the important formula A equal to ABC. This is mostly used for the quantitative analysis in the UV. Then deviation or limitation of Lamberts law. First is the real deviation. As a general concept is, as we are changing the concentration, absorbance also changes. Means if we are increasing the concentration, then absorbance has to increase, but this is not happening in practical. What is the reason? This is the deviation of Lamberts law. So three types of deviation they have given. First is the real deviation. What is happening in the real deviation? So at high concentration, the extent of solute-solvent interaction, solute-solute interaction or hydrogen bonding can affect the analyte, environment and its absorptivity. For example, at high concentration, the average distance between the molecule or ions responsible for absorption are diminished to the point where each particle affects the charge distribution of its neighbors. This solute-solute interaction can alter the ability of analyte species to absorb a given wavelength of radiation. Then second is the instrumental deviation. In this first is the polychromatic light. So mostly UV analysis require monochromatic light. It is not applicable for the polychromatic light. So what Beers says, Beers law strictly applies when measurements are made with monochromatic light or radiation. Second is the presence of stray light. This is also a part for deviation of the result. So what stray light is? Stray light radiation existing from a monochromator is usually contaminated with small amount of scattered radiation are called as stray radiation. Stray light often are the effect results of scattered and reflection of surfaces of gratings, lenses or mirrors, filters and windows. Next is the chemical deviation. The chemical deviation arises when an analyte associate, dissociate or react with solvent to produce a product with a different absorption spectrum. So here we are finished with the Lamberts law and deviations or limitations. Now we are starting with the types of transition in organic molecule. Three distinct types of electrons are involved in the organic molecule. So whenever the UV radiation bombard on any molecule, 4 types of transition involved. In that 3 types of electrons are involved, such as sigma electron, pi electron, and non-bonding electron. So wherever the saturated hydrocarbons or saturated molecules are there, sigma electrons are present. Wherever the unsaturated compounds are there, pi electrons are present. Whenever the non-bonding electrons are present, non-bonding atoms are present, non-bonding electrons are present. So here majorly 4 types of transitions are there. So mostly sigma bond, pi bond are the bonding orbitals. Then N is the non-bonding orbital. Pi star and sigma star is the anti-bonding orbital. So whenever the radiation bombard on any saturated molecule, the transition happening from bonding sigma orbital to anti-bonding sigma star orbital. This is called as sigma to sigma star transition. Then next is pi to pi star transition, in which in unsaturated molecule, whenever the radiation bombard on any unsaturated molecule, pi electron get transit from bonding orbital to anti-bonding orbital. That is pi to pi star transition happen. In the same way, when molecule having non-bonding atom, or example alkyl halide, in this molecule when transition happen, this type of transition is N to sigma star transition or N to pi star transition, where the sigma to sigma star transition, it requires highest energy, or it has highest energy and shortest wavelength. Then N to pi transition has lowest energy as well as longest wavelength. Next is sigma to sigma star transition. We can see this in detail. So sigma to sigma star transition, in this transition need high energy, it is very strong and occurs in saturated molecule. This transition requires very short radiation of wavelength, that is of high energy. The sigma to sigma star transition fall into the far UV region of the spectrum, that is below 200 nanometer, and are not relevant for the biological measurements. Such transitions can occur in such compounds in which all the electrons are involved in single bonds and there are no lone pair of electrons. Example, saturated hydrocarbons. The energy required for such transition is very large. The absorption band occur in far UV region is around 150 nanometer. Example, methane. The lambda max is at 121.9 nanometer, and for ethane lambda max is at 135 nanometer. The commercial spectrophotometer do not generally operate at wavelength less than 180 to 200 nanometer. This is the sigma to sigma star transition. Next is N to sigma star transition. This type of transition occurs in saturated compound containing one heteroatom has unshared electron pair such as alcohol, ethers, alkyl halides, etc. Energy of N to sigma star transition is less than sigma to sigma star transition. Saturated compound with lone pair undergo N to sigma star transition. The energy required for N to sigma star transition is generally less than that required for sigma to sigma star, and corresponding band appear at longer wavelength at near UV, that is about 200 nanometer. However, some compounds are known which absorb at slightly longer wavelength, such as CH3/3N, that is the tertiary amine. Here N to sigma star transition happen at 227 nanometer and sigma to sigma star transition happen at 99 nanometer. When absorption measurements are made in UV region, compounds such as aliphatic alcohol and alkyl halide are commonly used as solvents. However, these solvents cannot be used when measurements are to be made in 200 to 260 nanometer region. In such cases, saturated hydrocarbon which only give rise to sigma star transition, must be used. Hydrogen bonding shifts the UV absorption towards the shorter wavelength. These are some molecules where N to sigma star transition happens at a particular wavelength. Next is pi to pi star transition. Here in this type of transition, it occurs in the unsaturated molecule. This type of transition occurs at longer wavelength than sigma to sigma star transition. Alkene, alkyne types of compound contain this type of transition. In this type of transition occur in alkane, alkene, alkyne type or cyanide azo type of compound. It corresponds to promotion of electron from bonding pi orbital to an anti-bonding pi star orbital, and this principle occurs in many molecules having pi electron system. Example, ethylene exhibit an intense band at 174 nanometer and weak band at 200 nanometer. Both of these are due to the pi to pi star transition. According to selection rule, band at 174 nanometer represent an allowed transition. Alkyl substitution of olefins moves the absorption to longer wavelength. This effect is known as bathochromic shift. Trans isomer absorb at longer wavelength with greater intensity than the cis isomers. Next is N to pi star transition. In this type of transition are shown by unsaturated molecule which atoms such as oxygen, nitrogen or sulfur. This transition exhibit a weak band in their absorption spectrum. In aldehyde and ketone, the band due to N to pi star transition generally occur in the range of 270 to 300 nanometer. The carbonyl compound having double bond separated by two or more single bond exhibit the band due to N to pi star transition in the region 300 to 350 nanometer. In aldehyde and ketone, N to pi star transition arises from excitation of lone pair of electrons. So here we are finished with 4 types of transition. Then we will see effect of conjugation. Conjugation, as conjugation is increasing in any molecule, the absorption will shift towards the longer wavelength. So example here we can see last example ethylene molecule. Ethylene, here we are getting absorption at 170 nanometer, but as double bond increases, that is in butadiene, we are getting absorption at 217 nanometer. Like this is the effect of conjugation. Then solvent effect. So as one compound is there, we are dissolving in the particular solvent, we are getting the shift, because as we are dissolving the compound in the particular solvent, we can see change in absorbance of that molecule. So first is the red shift, this shift or bathochromic shift, this shift of absorption towards the longer wavelength. Then hypsochromic shift, this is the shift of absorption towards the shorter wavelength. Then hyperchromic shift, effect of an increase in absorption intensity. Then hypochromic shift, this is decrease in absorption intensity. So as we are changing the solvent, we are getting these types of shift. Next is chromophore. So generally chromophore is the compound which is responsible for absorption of UV radiation. It is called as chromophore. Auxochrome, it is not chromophore, but when it attaches to chromophore, its presence brings the absorption towards the longer spectrum. This is the auxochrome. Then application. Mostly UV visible spectroscopy is helpful for determination of chromophore, extent of conjugation, then conjugated double bond and single bond, then identification of unknown compound, elucidation of structure of vitamin A and K, as well as identification of compound in different solvent, then detection of impurities, qualitative analysis as well as